Our speaker is Mark Mayer. He has spent more than 40 years applying system engineering to problems ranging from sensor design to satellite constellation. He starts his career with Hughes Aircraft Company as a signal processing engineer. After completing a PhD in electrical engineering from the University of Southern California, he was a professor of electrical and computing engineering at the University of Alabama in Huntsville. And he's then spent 26 years at the Aerospace Corporation, rising to the rank of technical fellow. At Aerospace, his specialty was supporting new program starting up efforts, primarily in satellite system, but with period working on information and sensor systems. He is a co-author of The Art of Systems Architecting, and now coming out the 4th edition. He is currently professor and lecturer at University of Utah, teaching course on model-based system engineering, systems architecting, and aerospace systems. Let's welcome Mark. Sorry.
Hey, thank you very much. So as you'll see, I'm a little bit familiar with NCAR, UCAR, because what I'm going to talk about today caused me to spend a moderate amount of time at NCAR, working with our various stakeholder groups. And as you see, one of my co-authors on some of what I'll talk about here is Richard Anthes, who I'm sure many of you know. So let me give you a quick agenda and some introduction and some thoughts. So I'm going to say a little bit about one particular project. And I've worked on many projects applying systems methods over my career. And one of the largest and most significant was this so-called NOAA Satellite Observing System Architecture Study. So I'm going to give a little background on that. I'm going to talk about the principles, that is the basics of the systems method. And then I will talk about the application of that to the NSOSA project. And I hope that'll be familiar because, of course, it was largely about atmospherics with a certain amount of the oceans and other things kicked in. And then a few words about the application of the same sort of methods in other domains. And you know, this is the domain with which I'm personally the most familiar, the domain of satellite and space systems, because it's where I've spent the longest portion of my time in my career. But certainly these same approaches are used in a variety of other circumstances and other domains. So, you know, we already got a very nice introduction. I'm currently at the University of Utah, primarily involved with systems engineering and aerospace engineering graduate programs. I had been a technical fellow at Aerospace. Aerospace is a federally funded research and development corporation with responsibility for national security space. And while I had bounced around to a lot of different things because I was in the engineering division there, not one of the program divisions, I was attached to the National Oceanic and Atmospheres Administration for this NSOSA program for a period of well, not quite 5 years, 3 to 4. I started in electrical engineering, but I've mostly been known over my career for working in systems methods, and I'll cite a few publications and some things you might be interested in. So let me explain what's the NSOSA study. So the NSOSA study started back in the 2013-2014 time period, and it was an effort run by NOAA for the purpose of developing recommendations and plans for the generation of satellite systems that would come after the GOES-R JPSS program. So at that time, the GOES-R and JPSS programs were getting to first launch. So they were just starting the period in which they would replace the previous generation of programs. They were a long way away from achieving their full operational capability, but they were just starting. And because satellite programs have this very protracted development timeline, there was already discussion about what to do next. And this was driven both by the organization's exigencies and by external drivers saying NOAA needed really to work on its overall architecture. So generally, this was to broadly trade the fullest range of possible post-GOES-R and JPSS constellation architectures, which included terrestrial and space weather, and it included just building things that were kind of like follow-ons, building relatively minimal versions, and totally replacing the GOES-R and JPSS constellation concepts with entirely different concepts, either in the business or the technical side. So a key concept for understanding this is that we base things around what was called we refer to as the POR 2025, which by sort of happenstance is this year. This was the program of record, that is what we were paying for in the 2010s, that would come to full configuration approximately 2025, as it has. So in fact, today we have a system that looks approximately like this, and its primary chunks are, it has the two operational GOES satellites, the east and west location satellite. It has a warm backup satellite in the center position, and it has nominally one JPSS satellite in the polar 1330 crossing orbit. And all of this works in conjunction with international partners, many of whom are basically full partners in the system. And that includes the Europeans, who fly their Meteosat geostationary satellites, the Japanese and Korean geostationary satellites, the European geostationary satellite, which in this generation is known as EPS SG-A and B, and a few others that play parts in this, in particular satellites that do GNSS or GPS radio occultation measurements, the JASON sea level satellites, some Sentinel, and so on. And notably, the satellite systems at the L1 position, soon to become space weather follow-on, that play a key role in space weather monitoring. Now, this was fundamentally through the 2014-2018 time period. This led to follow-on activities that were then decisions on the GEO, EXO, and NEON programs. Those are now established programs, though of course there is currently direction to rather massively restructure the GEO EXO program. I'm not involved in those programs anymore, so I don't have any particular comment on that. I ended up moving to the aerospace office in Utah in 2020, where I joined an Air Force program at Hill Air Force Base, and then this past summer decided to take partial retirement from aerospace, but not entirely from working, and go to the University of Utah. And for those of you who would like to dig in farther on what I'm going to talk about today, there's a number of significant publications on this. There are two publications in the Bulletin of the American Meteorological Society, one in which I'm the lead author on the weather satellite architecting, and one on which Richard Anthes is the lead author that I'm also on, that is primarily about the development of the value model, which is one of the elements that I will discuss here. Now, the whole point of this is not really just to talk about NSOSA, it's to talk about the idea of system principles and the idea about addressing problems in complex systems in a particular perspective, the perspective of systems engineering and architecting. And some of the key aspects of this that I want to talk about are the deep attention to the problem domain. That is, even though we understand that the purpose of the effort is to arrive at solutions, we presume that when we start, we don't really understand the problem, and that immediate and obvious statements of the problem are probably wrong and will certainly need some level of deep refinement. It's an emphasis on objectives over binary requirements. That is, we are not emphasizing the idea of, just writing down a bunch of shell statements, but rather looking for the principle of cost value maximization, of understanding how is value delivered by things in the space of interest. And this is a very important aspect of this, because this means we're not just checking off satellite observation requirements, we're understanding how is value delivered to the environmental observation enterprise from what we do from space. And if you were to apply that to some other domain, the development of software, the development of air vehicles or something else, you would ask the same basic questions. What is the value chain that is enabled by, enhanced by, driven by what you produce in the sub-portion over which you need to do your study? We're not talking about just individual systems. We're talking about portfolios or families of systems or systems of systems, and that much of the investigation is characterized by variable technical depth. That is, it is not superficial, it's not necessarily narrowly deep, but it's some mixture of the two, and that we're going to have to dig deeply in a few areas to understand value, cost, risk trades. Now, what are the big elements? Well, the big elements are things like stakeholder concerns and need analysis, understand problems in stakeholder terms in depth, build a logical model. This is some sort of solution neutral model that is detailed in respect to functions and data, but not in respect to specific physical elements that we would buy. Build an expansive set of solutions, and this means not just something in our case, for example, not just geostationary and polar orbiting satellites, but rather a full possible range of alternatives, and 3 dimensions of which are the physical model, which is what you buy or build, the operational model of how it works, and the program model of how it gets built. And as I'll point out later, some of the important alternatives in the NSOSA space were business alternatives. They were questions of how we would build the particular systems, what business arrangements we would use to build and sustain them, rather than just what their physical consistency was. Analyzing consistency and completeness, evaluating the value model for cost-benefit comparisons, and doing it in cycles. And this is a very important one, that we start short. We do what we call a charrette, which is the quick and dirty end-to-end look, and then add details, and then cycle again, and add more details, and cycle again, and exploit the ability of iteration in the construct of a study in order to improve the results. Now, this was the sort of timeline that we used. And of course, the NSOSA program is a big program. A full cycle, say a GOES-R and JPSS cycle, consumes around $20 billion. That's a lot of money. That's an enormous amount of effort. And that means that it requires a requisite level of study effort to match that kind of potential investment. We started before 2014. We did a brief as-is study. For the first year, we conducted a series of what we refer to in this practice as charrettes, of short cycles of a month, 2, 3, 4 months each. We delivered results to the NOAA administrator at several times. Then the full formal study was set up. It was supposed to be set up directly tail-ended onto the end of charrette 3, but in practice, because of federal government bureaucracy and all kinds of other factors, it took us almost a year of bureaucratic effort to set up. Then starting in 2016, we really kicked off the primary study, and we did several cycles. We used some intensive design activities referred to as the CDC SAT, which was the Aerospace Concept Design Center. You can see those were done several times, that were used to develop both performance and cost values. And this continued until approximately 2018, which was the period where we did the final reporting, and then eventually wrote some papers. And then NOAA developed a series of exploitation and follow-on activities based on this. Now, let's talk a little bit about these sort of stakeholders and logical model. Because of the scope, the focus came to be primarily on objectives rather than functions. And the reason it is that because this is a satellite constellation, the set of primary functions was actually pretty simple. It was to collect a bunch of observations of the Earth or of space and of the sun, fundamentally a set of 38 terrestrial and space weather observations and 6 supporting strategic objectives. And when we asked where was the value came from the observation quality. Now, if you were doing this for example, the ground processing network and the ground processing software, it is quite likely that your value model would be deep on the functions and the variety and types of functions that were supported rather than just to measurements on those functions. And this is an illustration that you have to match the value model to the sources of value in the particular domain of interest. And for something like this, which is a rather stewardship, relatively mature satellite business, very often it's mostly about performance levels that are achieved rather than the functions, because the functions are pretty stable. Now, one of the big challenges was understanding where to establish objectives. And this is, again, part of the system principle of understanding where does the value come from. And there were opposite poles that were considered and that were not used. And at the top of the chain comes mission metrics. And these are mission metrics that are tied directly to what the total enterprise that consumes environmental data is producing. And a particularly strong source of these is NOAA's Government Performance Reporting Act materials that are reported to Congress on an annual basis, where they assert a set of, I'd have to go back and look, it's roughly 20 overall mission metrics. And a typical mission metric in that set is hurricane track forecast accuracy. And there's another mission metric for hurricane intensity forecast accuracy. And a metric having to do with aviation weather, which is a measure of skill over the organization's ability to provide visual versus instrument flight rules forecasts. And there's some in severe storms, and there's some in space weather, and again, a number of areas. Now, at the lowest level, there's also a large collection of individual data requirements. These are, like, for example, correspond to the current level 1 specifications on current satellite programs and the so-called CORAL, or Consolidated Observational User Requirements list. And there's hundreds of these, and these go to very specific environmental parameters and data records and the accuracy with which they're given. And we concluded that for the purposes of this study, neither of those poles was too useful. The low level was very specific, but that was its very problem. It was too specific. It was really tied to current operations, and there were hundreds of them, which is really too many to make a meaningful trade space over. The mission metrics were a very attractive target because they correspond directly to the funding stakeholders' interests in the system. But honestly, the difficulty there is that the current state of the art in understanding the performance of systems is not sufficient to be able to predict how much a metric, like let's say hurricane track forecast accuracy, is impacted by the quality of the observations. We know very well from history that better observations lead to better accuracy, but there really is not a quantifiable way of looking at that into the future. Now, for those of you connoisseurs of this area, probably say, well, wait a second, what about the OSSEs? And I would say, yes, in theory, you can get this kind of information from those, but in practice, very unreliable, at least when we're talking about working with data sources that are not being used today. So our intermediate is this kind of aggregated data classes, things like regional real-time weather imagery, 3D winds. And this was developed in large measure through the work of the Space Platform Requirements Working Group that was chaired by Richard Anthes, and that reflected extensive community involvement. So here's an example of what this looks like. So the NSOSA value model, as I said, had 38 terrestrial and space weather observational objectives. Those 38 terrestrial and space weather objectives are listed on the left-hand slide of this chart, terrestrial on the left, space weather on the right. And you can take any individual one and blow it up and get a bunch of attributes. And the attributes will look like things like ground projected instantaneous field of view, ground projected instantaneous field of view visible versus IR, near IR, sampling frequency or update rate, latency, and a variety of other characteristics. And these contain a set of fairly standard measures as well as a number that are typically developed for each of those individual ones. And the full NSOSA value model has this full set of attributes and measures for each of those 38 objectives in the left and the right-hand column on the left-hand side. And so this was this kind of intermediate, and that it represented the things that you can cost because they're what the satellite systems that we're paying for actually deliver. They're below the mission metric level, but they're well above the level of individual environmental data records. Now, strategic objectives, on the other hand, are those that are chosen to represent organizational objectives. They're typically non-technical. They're tied to the organization, and they're things that the organization is attempting to achieve. They also have measure sets. The 6 of them are shown here on the right. They were assurance of core capabilities, compatibility with fixed budgets, assurance of all capabilities, meaning goes beyond the core, programmatic flexibility and adaptability, develop and maintain international partners, and low risk at the constellation level. And there's a variety of ways these were done. These were also done at a level that were measurable and comparable between alternatives. Now, if we've built a value model, remember that I said the goal of this overall effort is not just to go out and kind of explicate what the value model looks like, but it is to actually come up with satellite alternatives. And in order to do that, we had to have methods for generating the satellite alternatives and eventually assessing and costing the satellite alternatives. And we ended up building what's kind of referred to as a modified Zwicky box. And this is kind of a menu thing where you have a, like a list of appetizers and mains and desserts. And in this case, and you pick one of each. In this case, you have a list of GEOs and low Earth orbiters and solar satellites like at L1 or L4 or L5, and other categories that I haven't put on here because, in fact, the diversity was pretty big. It would have included other non-polar low Earth orbiting satellites, medium Earth orbiting satellites, high Earth orbiting, highly inclined satellites. And we created constellations in these using a variety of design points. And our concept design center team used reference instruments at different performance levels combined with reference satellites to produce reference program concepts. So if I were to read through one of these, for example, this gives you sort of a sense of how this works. The constellation number C130 has a quick description. The C85 plus minus things won't mean anything to anybody, but it meant a lot to those of us who were working on the program, because it was saying, oh, we did this based on C85, and then we added or subtracted some stuff. And typically the way you do this is you start with I won't call it a random search, but a very wide search, and you look for constellations that have very favorable cost-benefit properties, and then you try to take the ones that have very favorable cost-benefit properties and you try to do things with them to figure out, well, how can I change those? How can I make changes on the margins or at the elements that will then improve even more what's already a favorable cost-benefit combination? So in the GEO1, we have a configuration known as 3D. And this goes back to a table of different, and you can say that was D within the third group of geosatellites. It has usually we gave it a quick name like a GOES Plus without solar or comm. So this meant it's a upgraded GOES satellite, and it does not carry the solar observation instruments or the communication payload. It is produced in a programmatic block size of 4. It sits in one plane, GEO. It is designed to have one satellite on orbit. It has a launch schedule. And again, what you see under launch schedule is a shorthand that referred to various schedules for production and launch, because we had constructed a variety of reference schedules for construction and launch that would yield particular levels of availability. It has a designated latency number, and then All the green, yellow, blue things down below it are quick references for which instruments are actually on board this satellite. And, you know, as was usual, when you get into a program, you start to shorthand a lot of stuff. I want to try to explain what each of those corresponds to, something that was well understood by the team as an instrument. The greens indicated that it was an instrument at the so-called expected level of performance. That is, it was at the performance level that was equal to what the community expected in 2030. Blue is indication that it is exceeds that level of performance. That is, it's at the highest performance level that had been advocated for. And a yellow indicates a significant dip from the expected level of performance. It's clearly below the expected level. In the second column is the second geostationary element, and it is a hosted imager. And what that means is that it doesn't have its own satellite. This is a business alternative, and we're mixing and matching business alternatives here too. So in this case, it means that we would buy a particular geostationary weather imager, the one known as VIGIST, which is a relatively low performance but lower cost and smaller one. And instead of building a dedicated satellite for it, it would be hosted on some other satellite in GEO. And hosting arrangements are, if not super common, are certainly well known, and many significant instruments and missions have been flown on another satellite. And this is often done, especially in geostationary orbit, because there's a lot of communication satellites in geostationary orbit, and it's very common for geostationary orbit satellite buses to have substantial extra available space, weight, power, and potentially communication bandwidth. So they're interested in taking on an extra instrument and getting paid for it, and to use up some of that extra satellite bus capacity that's frequently available. And this same pattern is repeated in the low Earth orbiting block, where there are satellites for different LEO orbits. In this case, for example, the LEO 1 block is a so-called sounder add-on. That is, it's an extra set of sounder capabilities, and it flies in two orbits, the traditional 1330 sun synchronous crossing orbit, and the 0530, which has historically been occupied by a US Department of Defense satellite, but in this case would not have been. It would have been occupied by a NOAA satellite. And then we also included space weather elements. So in this case, there was a comprehensive space weather observing satellite at the L1 position, and a roughly equally comprehensive space weather satellite dedicated to the L5, Earth-Sun L5 point solar observation position. And then down below, you can see the next one, C-136. It has a different combination. The C-136 has some interesting characteristics because it used a satellite concept called GT, which was a satellite which was capable of operating either in geostationary or in the highly inclined tundra orbit, which is an orbit that has a 24-hour period, but a high level of inclination, and that has preferential observation of the poles. Although depending on exactly which orbit is chosen, it can also have global coverage. This depends on a number of complicated orbital factors that I won't get into, but it was used for this combination flex placement in a so-called dynamic launch strategy between GEO and tundra. Now, I want to make a point that one of the things that we do here is this is not just something where we are studying the technical aspects, that is the satellite aspects of the solution. The program architecture is also part of the solution. That is, the decision on how to build the program, how to build the system, is equally a component of the analysis as is the system itself. And if you're scratching and saying, well, what are that sort of ought to imply there's a set of alternatives. What kind of alternatives? These are, for example, 3 reference program constructs from the NCOSE International Council on Systems Engineering Handbook version 5. They're known as the sequential, the incremental, and the evolutionary. And in the sequential is the traditional model, and this is where we figure out all the requirements up front and we build and deploy the system. And we do our learning after we've deployed the system. This is the classic waterfall model. The incremental model is where you also try to develop all the requirements up front, but you build the system and deploy it in increments. So here you might have built a version 1 and a version 2 and a version 3, and each of those is individually deployed to operations and allows you to have a learning cycle on each one. The evolutionary pattern couples that to the idea that we learn about the requirements each time we deploy. And so we deliberately start with something that we know or anticipate to be a partial representation of the overall requirements or objectives. And then we allow those to adjust each time we do a deployment and development and deployment cycle. And we do this with the deliberation of wanting to look at it that way. Now, the money outcome, what we're really trying to get to for this is we want to get to an analysis that looks like this. And this is a representation of what's called an efficient frontier analysis. Now, the way an efficient frontier analysis works is as follows. You make a two-dimensional plot, and you'll see that the two-dimensional plot is filled with little dots or stars or whatever. The x-axis of the plot is cost, and it can be with whatever cost metric you choose, whether it's life cycle cost or yearly cost or first year cost or whatever. In our case, we use what we call the relative cost metric. We won't get into in depth, but the point is it just shows cost relative to a reference case. And the y-axis is the metric of value. And ideally, it's the metric of value computed in a way that allows direct cost-benefit comparisons to be made. Now, logically, the more you spend, the more value you would get. So you would expect that there's sort of a general upward trend, left to right, bottom to top, meaning as you spend more money, you get better alternatives. Now, a really well-designed alternative will deliver the highest possible value for a given cost. So if you were to take the point cloud of all the alternatives you got and to form their convex hull, the boundary on the upper left is essentially the boundary of the most cost-efficient possible alternatives that you've been able to develop. And that's referred to as the efficient frontier because it says you're getting the most value for the least dollar by being on that efficient frontier. Now, I will point out that in any real complex situation where there are multiple stakeholders, you can't say that there's one single value metric. You might say there's one single set of value attributes, but the way they combine and relate with each other is dependent upon the particular stakeholder. So in fact, you might have to have many efficient frontier charts to represent that. What we do is we don't just look at the individuals, we also look at how they flow together in sets. And so for example, here, the alternatives can be roughly broken out and 4 different efficient frontiers can be computed based on 4 sets of shared decisions. And those are referred to as the legacy augmented, the hybrid, and the business alternative. The legacy was simply to say, let's keep things pretty much like they are today with US government owned and operated geostationary and LEO satellites in traditional orbits. And what we will vary is the performance of the instrumentation and the way in which we deal with some of the assurance characteristics. And that turns out to be a relatively less efficient legacy labeled curve. The 2 better curves are known as hybrid and business alternatives. And they were based on different split outs across orbits and the use of different acquisition concepts. What's particularly notable is that as you go to the relatively low cost end, the gap between those is pretty big. And as you go to the high cost end, the gap converges away. One thing this tells you is that as you start to invest a lot of money, that as you start to buy high capability, turns out you're a lot less sensitive to exactly how you buy it. Different ways of buying are kind of lead you to the same point. But when you're really stressed for budget, it turns out that it matters a lot, and that the choices you make a big difference in how much value you can squeeze out of a given amount of dollars. The legacy augmented was there to show the performance of a particular set of choices that I would call the sort of traditional choices for augmenting. And it turns out to have rather poor performance. That was a very controversial observation, and I could say a lot more about it, but I won't. I'll just say that it very specifically highlights, in this case, some very specific differences of view on which are the most important value contributors for future systems across the range of possible things that you might buy. Now, let me conclude by saying a few things about applications and other problem areas, because what I was trying to do here with this talk was to highlight and give you some references to the use of these methods in an environment, that I think should be relevant to all of you because it's fundamentally about environmental observation. But I'll point out that you can apply this to portfolios of software applications. You can apply it to portfolios of operational demonstrations, to specific product solutions or sequences, to technology road mapping. And I have written about that at some length. The paper that I referenced at the bottom of this slide is a paper I wrote fairly recently after this that kind of summarizes a broad range of application of these methods to some of those other situations. The building blocks remain the same: stakeholder analysis, logical modeling, value modeling, the broad generation of solutions, the kind of analysis, particularly a focus on efficient frontier analysis. Now, the details matter. So if I'm going to do solution generation and map out a solution generation for a family of software apps, it's not the same as for a constellation of satellites, because the design variables, the dials that you twiddle to generate different kinds of software are not the dials that you twiddle to generate different kinds of satellites, but they're folding into a framework of stakeholder analysis, logical modeling, and value modeling is very much the same. And it just means that you have to understand the details for that particular area. And that's what I had to say as part of my regular talk. I was trying to leave plenty of time for questions. And I'd be happy to entertain questions if somebody has something they'd like to hear about.
Yeah.
I got one, Mark. It's really interesting and really dense. So I'll have to think about phrasing my question appropriately. There was a big difference between the business frontier and then the augmentation legacy. But you told us, and I think I understand that a lot of those contentious things result in the attribution of value. So yes. Let me then go back to the first slide. We had 38 different observations.
Yep.
Were those 38 observations, were they handed to your committee, or did you guys have any input in selecting among those 38? Because it seems to me that they're pretty disparate, and how those 38 observations, different baskets of 38 observations would absolutely change those value frontier models.
Yeah, so, okay, a couple things. So first of all, the value metric, okay, that you saw in that chart was computed over all of the 38 and the 6 strategic objectives. All right, now, they're not in here, but if you look at some of the other papers I've referenced, for example, you can look at a version of that chart that includes only the space weather objectives, or only the terrestrial weather objectives.
Right.
Okay? And I mean, you could do others. You could say, well, I only want to see the objectives that correspond to the performance of medium range numerical weather forecasting, or, or the forecasting of tornadoes, or, whatever. Okay. And for sure, they give you different results. I mean, obviously you wouldn't, it would be nobody's shock at all that say, if I were to compare which observations I care about for space weather and for terrestrial weather, well, they're a very different set. because the terrestrial weather is basically half of the 38 and the space weather is the other half of the 38.
Right.
Okay, so I'm just saying, so that's a clear thing. No cure for that. That just reflects different stakeholder perspectives. Right now, when the space program the space platform requirements working group was in operation and meeting occasionally at NCAR, one of the things that they were tasked with sorting through was development of a prioritization amongst the 38. Okay, and then we included a prioritization amongst the 38 and the 6 when we took it up to NOAA leadership. Obviously, that wasn't done without the generation of some controversy and some level of dissenting opinion. I will say, however, that what I found interesting was actually not the presence of unanimity, but the presence of a moderate degree of pretty substantial consensus, which for sure not everybody agrees with, but certainly the people on the SPRWG came to a significant level of consensus about some of these things. Now, there's some technicalities in this, which I'm not really gonna have time to get through, because when you do this kind of judgment, how you do the judgment is very important. And if you try to make this judgment on the basis of, tell me which of these 38 things has the highest priority, I guarantee failure. Absolutely will never happen. All right. And the reason is that if your tradable range for every one of the 38s is from 0 to arbitrarily good, you can't say anything about relative priority, because the priority of having a minimal amount is not the same thing as the priority once you have large amounts. That is your design. I use this in class. When I teach this, I call the analogy, I call this the desert island case. Okay, the food, water, entertainment analogy, which is you're stranded on the desert island and you'd like to have water, food, and entertainment. If you have none of each, it's pretty clear that you have the water as your highest priority. If you have plenty of water and food, it's pretty clear that entertainment is your highest priority. What's your highest priority depends on your level, and you have to elicit that understanding of how priority changes as you draw through levels. And then in order to make that a useful thing for making a judgment like this, you have to make decisions about what the tradable range is. That is, what's the lowest you're ever interested in going and what's the highest you're ever interested in going. That particular chart that I showed you reflects the consensus judgments on those trades given a definition of the tradable range. Okay, and if that tradable range changed, you might well get different results.
Thank you. That's really helpful and interesting. Thank you.
Sure.
Any other questions? Any question from people online? Yeah, so go ahead.
Hi, Mark. Thanks for the presentation.
The invitation.
Yeah, of course. I was wondering if you could talk a little bit about how the systems engineering and systems architecting differs when you're applying it to software-centric systems as opposed to hardware.
Okay, so there's a couple things. Some of them are, I guess I would say, nothing is fundamentally different, but lots of things are different in the details. Okay, so a couple things in details. One is that in general, things that you're doing in software tend to be functionally and data rich compared to building satellites and the like. So when you work on your problem understanding, you frequently have to struggle with the question of, instead of saying, do I really care about having my imager with a resolution of 100 meters or 400 meters, when I look into the atmosphere? That may not really be a meaningful question for software. It tends to be more questions like, do I care about which kind of data do I care about? And which functions? And do I have the function or do I not have the function? build something and incorporate it, or did I not get it at all? Because the software tends to be much more malleable that way, and the data tends to be much more malleable. The satellite biz, you're working with long timelines, and your investments are very sticky. Okay, once I've built it and flown it, it's there, and I'm not going to get to change it for a long time. So you have to think about things in a way that emphasizes, what's the lasting value that I get out of it without changing it. In software, usually you're thinking about changing it very frequently. I mean, that's sort of one of the great positives of software, is the fact that it can turn over relatively fast. So oftentimes value is much more in the optionality for what you can do next and next and next, as you get a lot more what I would call option value than the absolute value of saying, oh, here's this piece of software I've got today. What's the delivery I get today? Which is what I really do with satellites. I say, once I get it and I fly it, I better be happy with it for a long time. Whereas very often, a lot of the value on software comes from what enables me to do the next cycle and the next cycle and the next cycle. Now, again, it's still a value assessment, but it's in the detail of how you do it is different. The other thing is I guess I'll call it a simple thing, is that when you're doing a satellite architecture, a satellite systems engineering, the thing you're working on is very clear. You can go down, you can look up in the sky and maybe you see it pass overhead. You can look at it in the lab and you can say, well, there it is. This is how many boxes it has. This is the solar panels that it's got. If I want to say what's the different alternative, I can characterize it pretty clearly. In software, often one of the first things people have to come to grips with is really deciding, what the hell is it? How do I make a catalog of it? Am I cataloging the applications? Am I cataloging the algorithms? Am I cataloging the runtime services? Am I cataloging the different kind of data files I can input and output? What are these things of interest that I want to actually track? And sometimes, we usually don't think of that as being a step, because in the physical world, it's so obvious, nobody has to call it a step. I don't have to call it a step to say, what's my robot? Do I have one? But oftentimes in a software intensive one, I have to take a first step, which is to think fairly deeply about, what are the elements that I care about? Are they applications, services, computers, file types, use cases, scenarios? What's the natural granularity of things that matter? One of my guidelines that I always say is to think about what you pay for. Okay, if you have to buy it and you have to pay for it, it's probably something you ought to be concerned about. So sometimes that's a helpful way of, getting around some of the questions of identifying granularity.
Thank you.
Okay.
Any other questions? No. Let's thank our speaker again, and hopefully, thank you so much. It's very interesting talk.
Thank you very much. Thank you very much for the invite. Obviously, I don't live in Boulder, but I was very happy to get to know all of you again. I enjoyed my association with UCAR in the past through Rick Anthes, and I've been really happy having Sode in my class this term. So knowing you guys you guys are in a very interesting group. So I wish you all well.
Thank you.
Bye.